Good morning, everyone. Back with me, Emma again. So today we are going to be making a fireproof balloon using materials that we can commonly find around our house, or you can purchase for a couple bucks at your local grocery store or Dollar Tree. So for our fireproof balloon, we are going to need today 2 balloons. These are just regular latex balloons. Some water in the water bottle, preferably one from a tap or a spigot. It'll make things a lot easier. And a flame of some sort, regular candle. Lighter works too, either way. Okay, and preferably a bucket or a bowl. We're just gonna need that today, maybe just to hold things in place so things aren't rolling around all over the table. So today, I am going to be using this little tea candle. I have it in this little container, only because it's easier for me to pick up with gloves for today's purposes. Okay, so back to the experiment. So the objective of today's experiment is to help develop a more thorough understanding of what specific heat and high heat capacity are. Specifically, how our water has a rather high heat capacity and specific heat when compared to that of air. But let's back up a little bit first. What exactly is heat capacity and specific heat? They sound really similar. Are they the same? How are they related? What's up with them? So, heat capacity is the amount of heat required to raise the temperature of an object by 1 degree Celsius. Heat capacity has the units of joules per Celsius. See? Okay. Whereas specific heat is the amount of heat required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Specific heat has the units joules per gram per Celsius. See? All right. So, as we mentioned a moment ago, water has a high specific heat when compared to that of air. The specific heat of water is about 4.18 joules per gram. Written up there, right for you, nice and easy to read. So, water's specific heat is only about 4 times that of air, meaning air measures about 1 joule per gram per Celsius. All right, so now that we have that distinction and we understand them and how they're going to relate to our experiment, let's begin. All right, so first we're going to take one of our balloons and blow it up. Either one works, just grabbing a random one. All right, so I knew I was gonna have trouble blowing up this balloon. So what I did, I had actually blown one up previously. You wanna blow up your balloon, not super duper all the way, but pretty much full of air. And then you're gonna wanna tie it in a knot so it's secure at the end. Like I said, I just did this before, just because I had a bit of difficulty and I didn't waste a whole bunch of time trying to blow up the balloon on video. All right. Then we're gonna take the other balloon that we had. And what we're going to do is that we are going to then fill it up with that of water. So this will be a lot easier if you go to your sink, either in your bathroom or your kitchen or even outside where you attach the hose and attach this to that to add some water to it. Just for the sake of time today, I actually already filled up a balloon with some water, just because I had to travel a bit of a distance and I didn't want to take the computer on an adventure and potentially trip down the stairs and break it. So I hope that's okay. So when you are filling up the second balloon with water, you want to make sure that you are using either room temperature or cold water. You don't want to be using boiling hot or super duper duper hot water. One, safety, and 2, you're going to see what happens next in the experiment. When you're filling up the balloon with water, you want to make sure it's about maybe 1/4 of the way full ideally. Have some air up top. You definitely want to have some air. You don't want it to be full up to the tippy top, say, with water. As you can see here, it's full about 1/4 of the way with water. It's just regular tap water from the spigot outside. All right. And I'm just going to put it back in the bucket. And meanwhile, this is just to help keep balloons in place so they're not rolling around. Whoops. Okay. So when you're done filling that up with water, and make sure you have adequate amount of air, just tie it in a knot to make it nice and secure so nothing escapes. Okay. So next, we're going to take our flame. How I said in this situation, I'm just going to be using a regular tea light candle from Dollar Tree, nothing special. And I am going to light it up. As you can see, right down here. Okay, so it's just going to, a heat source of some sort. You can use that of a lighter, that of a candle, whatever, it's all the same. Okay, so the first balloon that we had blown up strictly with air and tied in a knot. There's no water, just air. As you can see, no water. What we're going to do, we're going to actually hold it over the flame. Now, it doesn't have to be directly on top of the flame itself, but we want it kind of close to the flame and gradually so. So what we're going to do is first start maybe about a foot or so away from the flame, and we're going to gradually bring it closer to the flame, okay? Just super duper gradually. And as we're going to be moving the balloon closer to the flame, you can actually see the latex starting to, the exterior of the balloon, starting to change shape because it's actually melting the balloon material. And we're going to be approaching do you see how it's changing shape? Right around this area. And we're going to be continuing doing this as it gets closer and closer. See it again changing, how it was going inside? I'm sorry, having an indent. We're going to keep on bringing it closer and closer until it pops. Whoop. Okay. So in doing so, the balloon accidentally put out the candle, probably because there was a big gust of air. No biggie. What we're going to do next is just relight our candle. The second portion. Okay. So you're probably thinking at home, yeah, sure, Emma, I knew that was definitely going to pop. I mean, that's just what happens. What did you expect? Okay. Well, that was kind of for a comparison for the second part. The second part's super duper cool. Okay. So we're going to take our balloon that we filled up with water, about 1/4 of the way, rest of it with air. And we are going to do the same exact thing that we did with the first balloon. So we're going to start about a foot or so above the flame and bring it closer and closer and closer and slowly lower it over. Now, as you're going to notice, even though we're going to get pretty close to the flame, the balloon's not going to pop. Ready? Starting about a foot over it. You can also tell that the balloon is not going to be changing its shape. See how there's no change in the shape at all? No indentation, nothing. We're super duper close to the balloon now, and nothing's happening. See? It popped before. We saw it actually shrinking in the latex before and changing the shape of the balloon, but we're not seeing that here. See, once again. We were much closer to the flame this time and for a longer period of time, and nothing happened to the balloon. It didn't change shape. Nothing. Didn't pop. Okay, just going to put that aside.
Hey, baby.
So, you're probably wondering, what was going on with that? So the reason behind it is water is super awesome at soaking up heat. Specifically, the heat from our flame. So we saw that the balloon's material, the latex, wasn't melting at all. It wasn't changing in its shape, size, nothing like that. See? Super duper close. Nothing's happening to it. So the reason behind this is because the thin latex material of our balloon actually allows the heat from the flame to rapidly pass through and heat the water that's on the inside, heat it up. So you're probably wondering, why didn't the balloon with the water just pop as it was held over the flame for a pretty long period of time? I mean, you did that numerous times. You got super duper close to the flame. You missed it. See it again. Nothing happened. Didn't change, didn't pop, nothing. So the reason behind that is because the water that's closest to the flame, as we can see down here, the water that's down at the bottom of the balloon, It actually winds up heating up a bit. And in doing so, the water that's heated up starts to rise. And in exchange, the cooler water that was in there replaces the heated up water that had since risen to the top. So that cooler water replaces at the bottom of the balloon. So this cycle happens super duper fast. And it continually repeats itself. It's a very repetitive cycle, and that's actually what keeps our balloon from popping. So the balloon will eventually pop when the heat of the flame is greater than the water's ability to conduct heat away from the thin latex. Basically, the presence of our water allows the heat from our flame to be absorbed by our water and not cause the latex balloon to break immediately, or even after a couple minutes or several attempts, as we saw. So when we hang the balloon filled with water over the flame, you can see that the water, just down at the bottom, is staying in close contact with that of the balloon. See, it's clearly pushed up against the push-ups against very tightly against that of the balloon. And we can see that it's providing a nice, reliable thermal contact. So the exterior of the balloon is heated by the flame, like the exterior of this portion of it. It also winds up heating the water as well. As we had mentioned a moment ago, it actually winds up heating up the water inside of the balloon due to the heat transfer. So we've learned previously in chemistry and a couple of videos ago that water has some pretty stellar and unique properties. We'll get this. So water's high thermal conductivity allows for the rapid distribution of energy throughout its entire volume, meaning that we aren't just heating up the exterior of the balloon, not just this part, the part that we can see and touch, but rather all of the water that's inside, as well as the exterior and the interior of the balloon, basically all of it, as well as the air, because as we remember, the air also occupies space as well, and that's also part of the balloon. So knowing this, and water's boiling point, which is 100 degrees Celsius, so we know that it's below the melting point of that of our latex balloon. Combined with water's high heat capacity, it makes it pretty much impossible to heat the entirety of the balloon, of both the balloon, all of the balloon itself, interior and exterior, as well as the water inside of the balloon super fast. All right, so let's bring it back to how our experiment demonstrates the difference between specific heat of our latex balloon and heat capacity. So we can see that's dependent upon the mass of the material present, or latex balloon, as we have the water inside of the balloon absorbing the heat energy from that of the flame, with a smaller increase in temperature than that of air would. The lower temperature change of the water actually keeps the temperature below the melting point of the balloon, preventing it from popping. So basically this means that the water inside of the balloon can efficiently protect the balloon from the flame for a decent amount of time, as we saw. Super duper close, decent amount of time, nothing happened. No changes, shape of the balloon, no deformities, it wasn't expanding, wasn't shrinking, nothing. Not even an attempt to pop. So in doing so, we saw that our balloon didn't pop, didn't change, nothing, remained exactly the same. The protection that the water is offering will last until all the water that's inside of the balloon will boil away, and once it does so, the balloon will pop. And just as a quick little reference, once over, if we wanted to know the specific heat of water, it is 4.18 joules per gram per Celsius, and the heat capacity of water is 4.184 times 10 cubed joules degrees of the Celsius, as you can see right there. All right, well, thanks for joining me today. And if you have any questions, just comment below. Thank you.